So in this lecture, we will continue the fundamentals of energy transport. And I would guess this is set number 4 of the lecture notes. And let me call that actually part 1, so we can break down that set into multiple parts. So we have short recording videos. So recapping what we got during set number 3 of the lectures, we were able to introduce the relationships for or the correlation that we use for calculating the rate of heat transfer, Q, using 3 different mechanisms: conduction, convection, and radiation. So under the conduction, we introduce the equation of Q equal minus K A partial T by partial X. And this is Fourier's law, right? And we agreed this is going to be good for a plane surface, whereas the Cartesian coordinates is used, X or Y or Z, depending on the direction of the heat transport. If we move to cylindrical shape, I introduce the equation of minus K times A partial T by partial R, whereas X and R are the direction of the energy transport. And this is good for a cylinder. And we were able to simplify this equation by a very simple assumption to assume that temperature change within plane surface, looking to the projection dimensions here. This is the direction X. This is X equal 0, X equal L, whereas L is presenting the thickness of this wall. And I have one face here, or that surface here, is at elevated temperature TH. This face here is at lower temperature TL. And because of that driving temperature difference, we are expecting heat or energy will transport through the solid body, which has a thermophysical property of K, and that quantity Q can be calculated by this equation. And because we don't know that form or the formula for the temperature as a function of X, we assumed for simplicity that the temperature change would be linear, which means that dt or partial t by partial x is going to be simply the slope of that line. Slope is measured from the positive direction here, so that's the slope, or you can measure that slope and put negative sign. So the negative sign of that slope here, which equal to delta t over that thickness L, that's the angle here. And the sign will be canceled out because we are getting this instead of this angle. So tan, this angle is presenting the slope. So the equation end up to be Q can be written as K A, and this will be TH minus TL divided by the distance between these two faces here, which is L. And that's the most simplified form of Fourier's law. Okay, so that's what we did originally for the conduction. Number 2, we introduced the convection heat transfer. And we introduced actually Newton's law of cooling. And the equation was very simple, that Q is equal to H times the surface area times either T surface minus T infinity, which is the surface temperature minus the fluid temperature, or T infinity minus Ts. Here, we don't care about the direction, it's just the quantity of heat transfer. If you want to remember more details about these two mechanisms, go back to the previous set 3 of lectures, and you can get more information. Then the third one was radiation, which I'm going to skip right now because, as I mentioned before, radiation is not really in the focus of this course. So these are the 2 equations that we're going to use all the time. So, and we covered an example that combined conduction, convection, radiation, but let me actually try to combine these 2 specific mechanisms here in a simple idea. Let's assume that we have a surface or a solid surface with thermal conductivity K. The thickness of this wall is L. And here's the X direction that we use all the time. So X equals 0 is here, X equals L is here. And now I'm telling you that the left face of that body Again, please go back and check how we converted the 3-dimension block into that projected surface. So this line is presenting the face that's going inward the page. So when I draw here, we have T infinity 1 and H1. This means that there is a fluid as a thermophysical property or convection heat transfer coefficient H1 and at a temperature T infinity 1. Then the other face of that wall is exposed to another fluid with thermophysical property H2 and temperature of T infinity 2. Let's assume that T infinity 1 is much, much greater than T infinity 2, which means that I'm already having a temperature difference. I'm having a driving force that's going to drive energy because I have a hot fluid in this side and cold fluid in this side. So how the energy would transport in this case here. So what's going to happen there is this is a fluid going over a solid surface. So there is a mechanism of heat transfer associated with the motion of that fluid. We call that convection. Now the energy is standing by on that face, but we are expecting this face temperature will be higher than this face temperature. So that driving force will push the energy to go through the solid body by conduction. And now the energy is waiting on the other face of that solid body. And we're still expecting that, because we are expecting temperature is going to decrease this way. So this temperature is higher than this face temperature. This temperature is higher than this face temperature. Now I'm having this face temperature is going to be higher than the fluid temperature. So I'm going to have another driving force to push energy out. And this is going to be by convection because we have a fluid in a motion here. So we have conduction, convection, conduction, convection. So what I need to do is to apply Fourier's law here. Newton's law of cooling here. I want to apply Newton's law of cooling here. And I need to apply Fourier's law in here. So three equation has to be used. So in a simple language, I'm going to call that surface here at TH. I'm going to call the temperature of that face here TL. I'm going to put it lower a little bit then because I know that it's decreasing that direction. So the governing equation to solve this problem is going to be simply saying that Q is equal to H1 surface area 1, which is the surface area of that face going inward, right? So let me draw that in 3 dimensions for the last time. I'm not going to do that anymore. We're just going to stick to the 2 dimension all the time, a projection of that body. So that's this face here is presenting this face here. So TH is presenting the temperature of that back face in the back. And TL, which this one is going to present the temperature of that face. TL, I'm going to put that dash because I don't see it. And this is TH. Okay. And now the fluid is going over that face and the fluid is going over that face. So according to the convection equation, Newton's law of cooling, this is the surface area, or sometimes we call that the contact area. And this is presenting the area of the back face here. So that area of the back face here is surface area 1. This area here is surface area 2. So if I'm applying the convection heat transfer coefficient, the convection heat transfer equation in that back area here, I'm going to have H1, which is the fluid the convection heat transfer coefficient of the fluid on the left side, and T infinity 1 here, that's the temperature of that fluid. And this side, I'm have T infinity 2. I'm having H2. So now I just transformed the 2-dimension projected problem into a 3-dimension problem. So Q is going to equal to H1, surface area 1. Now I know the heat or the energy is going in that direction. So I'm expecting that T infinity 1 higher or larger in value than TH. So this will give me the value of the heat transfer that's going to be transferred by convection from that hot fluid to that back face of the cubical shape here. Then we always assume that we have steady state, unless otherwise is mentioned. If we have a steady state, do you guys recall the energy balance equation? What is in equal what's out. So whatever that quantity of energy that went to that face is going to be the same quantity of energy that got to transport from this face to this face. Steady state, nothing is stored. Coming in, leaving out. No exceptions. Okay? only when we don't have a steady state or we have unsteady state, time comes in the game, and now energy stored is going to be there. So I cannot say that En equal E out. And this body also doesn't have any internal heat generation source. So whatever is going in is going to move inside, then it's going to leave. That's a steady state when you don't have any heat generation and you don't have energy stored. Steady state means that energy stored is 0. The problem doesn't mention anything about energy generated. So if you go back to the energy balance equation, you will find that En should equal E out. En, energy N, should equal to the energy out. So it's going to continue the same quantity as you go inside the body and leave from the other face, which means that the same Q, I'm not going to put 1 and 2, it's the same Q, going to transform through the solid body by conduction. So I'm going to apply Fourier's law, K times A times TH minus TL divided by the distance between the two faces, which is L. Now, we need to look to the definition of the area in the conduction. It is the area perpendicular to the transport, energy transport direction. So energy is going this way. What is the area perpendicular to the arrow here? It is the same AS1 or AS2. By the way, AS1 and AS2 are the same. So this is AS1, is the same as AS2, is the same as A for the conduction. So A is going to be always the same, okay? So then I now have that energy transported from this face to this face by conduction. Then I'm going to take that same quantity of energy leaving by convection. So that same Q is going to go H2 AS2 times, now energy is going this way, so it's going to be TL minus TH2. So these are the 3 governing equations to solve this problem. It's going to depend what is given, what is required, but at least these are the 3 equations that's going to be implemented to solve that problem. So you have to apply this equation multiple times. And I can complicate things. I can have actually your house wall covered by a layer of a paint or concrete, then a layer of paint. Then the house inside is exposed to a fluid. And the house outside is exposed, the house wall is exposed to another fluid. So now I have 3 layers intact or in contact, 3 solid layers. So this would be a wood, so it has a K1, then a cement layer, K2, then maybe a painting layer, that's K3. Each one of the 3 layers has different thickness. So that's L1, L2, L3. Now, if you want to solve that problem, how many equations are you going to write down? I'm going to write 1 equation for convection, 3 equations for conduction, because the 3 layers, they have different thickness, they have different thermal conductivity, and another equation for convection. So the governing equation to solve that problem are actually 5 equations. So think about it if you have multiple layers here. So it's not wrong, but it's very time-consuming approach to solve very simple heat or energy transport problem. And that's going to be the motivation to look into a much simpler way to do these problems. It's not going to take a few seconds to do it in a simple way of analysis, which we call that technique the thermal resistance analysis. It is very clear from the name that the analysis or the method is driven from the resistance, which means it's actually driven from the electric circuit class. If you recall, if you have electric resistance R, to drive a current through that resistance I, you need to have a potential difference, delta V, between these 2 nodes here, right? And the governing equation is actually Ohm's law, right? Which is delta V is simply equal to I times R. Or you can manipulate the equation a different way. If you want to calculate the current, you divide the potential difference over the resistance, right? Or if you want to calculate the resistance, you can get delta V over I. And this is totally a circuit analysis equation. That's Ohm's law, right? Then we as thermal engineer decided to do something very equivalent here. Said, okay, instead of having a electric resistance, we're going to have a thermal resistance. The current that we drive through that thermal resistance is actually the heat transfer, which is Q instead of I. And the driving force is not going to be a potential difference. The driving force is going to be the temperature difference. So now R became R thermal, I became Q, and delta V became delta T. Now I can apply Ohm's law with my new symbols here. So the temperature difference delta T is simply Q times R thermal. If you want to calculate Q, you divide the temperature difference by R thermal. If you want to calculate R thermal, you simply divide the temperature difference divided by Q. That's a similarity analysis here. Then we took advantage of this equation here. Then we looked back into the conduction and convection equation that we had. Also, we can apply that for radiation, but it's not going to be considered here. So now go back to the Fourier's law. What was the equation is? It's Q equal K times A TH minus TL divided by L. So I can simplify this equation as Q equal to thermal conductivity K, the area that's perpendicular to the heat transfer Q, times temperature difference between the hot and the cold surface divided by L. Great. Let's try to drive this equation out of this equation. Let's arrange this equation to this format. So if I want to get delta T over Q, I will have delta T over Q is equal to L over K A. What is the name of that ratio here? It's the thermal resistance. So we said I can define a thermal resistance basically for what is the source of this equation here? That's a conduction. So thermal resistance of a conduction can be defined as the thickness of the wall, L, remember, divided by the thermal conductivity times A, which is A perpendicular to that Q. So now I can calculate a thermal resistance that's present a single wall. So I can have that wall here that has TH, has a TL, has a thermal conductivity K, has a thickness L, and I can replace that body here with a very simple resistance like this. The two nodes are at TH and TL, and that's what gives me delta T here. Remember, delta T is TH minus TL. And this is a thermal resistance that can be calculated from thickness L divided by K times A, whereas A is the area going into that page here. And what's moving inside that resistance is actually the heat transfer Q, which is driven from the hot wall to the cold wall. So I did simplify a single wall conduction by a single resistance. Okay? So now, if I go back to a problem with multiple layer conductions, so let's assume go back to this is my house wall covered by a cement layer, covered by a painting layer, whatever number of layers here. We said this is K1, this is K2, this is K3. Let's assume that inside the house is warm, so that face is at TH. The outside face of the wall is cold, TL. So what we're gonna do, we have L1 for that thickness. We have L2 for this thickness. We have L3 for this thickness. I can represent this complex problem into a much simpler thermal resistance circuit. How? I'm gonna have two driving pressure here. Two driving pressure force, which here is the temperature difference, TL, TH. Each individual layer will be presented by a resistance. So this is wall 1, this is wall 2, this is wall 3. So I'm going to present that into 3 resistances. And go back, think. We know that heat is going to go by conduction here. Heat is going to go by conduction here. It's going to go by conduction here. Q, Q, Q. And all of them are equal, correct? All of them are equal. Steady state, no internal source of heat generation. So energy in equal energy out. So whatever is going is going to be constant all the time. Do you recall from the circuit analysis what kind of arrangement of resistances that has the same current going through? That's correct. When the resistances are connected in a series, which is telling me that I can present each one of these walls by a resistance, but keep these resistances connected in a series to guarantee that the current going through all of them is the same. So I know that phase will be at a given temperature. That phase will be at a given temperature, and temperature is going down from here to here. So I'm gonna present a node and a node here. Let's call this is T1 and this is T2. So I'm gonna call that node T1, this node is T2. Between each two nodes, I'm having resistance. This is a resistance that presenting the first wall. I'm gonna call the R1. Another resistance that's presenting the second layer, R2. The third resistance is presenting the third layer, R3. Now, how to calculate R1? This is your equation here. L over Ka. So if I want to calculate R1, it's going to be the thickness of the first layer divided by the thermal conductivity of the first layer times A of the first layer. Again, if I extend that body into three-dimension drawing, which I don't like to do, but you have to keep your imagination on, you'll find that the area perpendicular to the Q is always the same as you go, right? These are three stacked layers next to each other. All of them, they have this is the area we're looking for. It's the same along the three layers. So it's going to be only A. Then I want to do the second resistance. This is presenting conduction through the second layer. L over Ka. Second layer has a thickness of L2, thermal conductivity K2, and the area is still A. Third resistance. It is presenting conduction in a third layer. The equation of conduction thermal resistance is the thickness of that layer, L3, divided by thermal conductivity, K3, times A. Now I have the three resistances calculated. Then what I can do, remember, the electric current going through the three resistances is the same, Q. Okay, now how to calculate Q? Go back to this equation. How we can calculate Q? Q, you pick delta T over the thermal resistance. Q is to pick delta T over the thermal resistance. Now I see multiple temperatures and multiple resistance. Which temperature difference I should pick? Again, these are series resistances, which means that if you calculate the current in this resistance, it should be the same in this resistance, should be the same in this resistance, should be the same going through all of them. So that's your choice now, depending on the given information of the problem. One would say, I can actually calculate Q from picking delta T over thermal resistance. Let me write down the general equation. One would say, I'm going to pick TH minus T1. That's your choice. In this case, you have to divide by the resistance between these two nodes. So I'm going to divide by R1. Someone else said, no, I don't like this equation. I'm going to pick TH. I'm going to pick T1 minus T2. That's your choice. You pick T1 and you pick T2. What's between them? It's R2. You divide by R2. And you see that I'm putting the equal sign all the time. One would say, no. I'm going to pick T2 minus TL. I said, okay, you have to divide by R3. One would say, no, I don't like any one of these. I'm going to pick TH minus T2. Said, hey, stop here. You pick this temperature and this temperature, correct? You have to divide by the resistance between them. Between these two nodes, I have two resistances connected in a series. What is the equivalent of series resistances? You add them up, correct? So this will be actually divided by R1 plus R2. Now pick any two random temperature values. Pick TH minus TL. Now, what's in between? 3 series resistance. I'm going to get the equivalent by adding up all of them. And this is the most common problem here. To use any one of these, you have to know the temperatures, right? To calculate Q. Usually, we will only give you this temperature and this temperature. So if you are given only these two temperatures, you are forced to use this equation. So I can force you in the problem to calculate all the resistances. Then, if you calculate Q from this term, so I know the value here, I can use Q with this equation, I can calculate T1. I can use Q with this equation to calculate T2, and so on. So I force you with these two only temperatures to calculate all the resistances, to get Q from this formula. Then I ask you to calculate T1 and T2. You take that Q value, it's the same, and you put that equal to any one of these terms to calculate the missing temperatures. If I take this value with this value, this ratio with this ratio, the only unknown would be T1. I will get T1. If I take this ratio and this ratio, I can get T2. Or if you take this one with this one, you can get T2 because you already calculated T1. But keep in mind, if T1 is miscalculated, T2 will be miscalculated. So I always prefer to pick ratios with mostly common information. So if I take this ratio and this ratio, TH and TL is already given information. So T1 is going to be okay. Then if you take this one with this one to calculate T2, now you are not using T1 to calculate T2. If you mess up the calculation for T1, it's not going to mess up the calculation for T2. So I hope now that explains how to convert multiple layer conduction into simple thermal circuit analysis and use that analysis to calculate either the heat transfer rate, Q, or you can calculate the interfaces temperature like T1 and T2. Okay? So that's how we do it with the conduction. So instead of now writing 3 equations, and I need to solve the 3 equations together because each equation will have multiple unknowns, right? If you write the equation for conduction for the first one, what's going to be? It's going to be K1A TH minus T 1 over L1. That's Q. The other equation, K2A T1 minus T2 divided by L2 equal Q. The third equation, K3A T2 minus TL divided by L3 equal Q. Now, each one of these equations has unknowns, right? I don't know what's Q, I don't know what's T1. I don't know what's Q, I don't know T1 or T2. I don't know Q or T2. You have to solve 3 equations together, system of linear equations, to get these unknowns. But now, with the thermal circuit analysis, I don't need to do that. I'm telling you, this is only take like less than 10% of the total time that you need to calculate, do calculation like this. Okay? So that's the beauty about the thermal circuit analysis technique for conduction. Okay? Now, what about convection? That's the second one. So we know how to do that for conduction. We need to do that for convection. Again, what is the governing equation in convection? Q is equal H times the surface area times T surface minus T infinity or vice versa. Doesn't matter. Let's simplify the equation. Q is equal H surface area delta T. Now, go back here. Rearrange the equation to have delta T over Q. So I can take delta T over Q is going to equal to 1 over H surface area. What is this? This is the definition of thermal resistance. But in this case, the thermal resistance is driven from the Newton's law of cooling, which means that I can calculate thermal resistance, but for convection, it's obvious because the equation has H into it using 1 over H surface area. Whereas H is the convection heat transfer coefficient and AS is the surface area. Sometimes we call that the contact area. Contact area. Whereas the fluid is becoming in contact with the solid. You guys remember the boiled egg and the air going over? So the air will be in contact with the surface area of the egg. So we're going to use that as a surface area. If you have a cylinder and it's cooled by a fluid going over, you're just going to count for the surface area here, whereas the fluid is becoming in contact with the solid surface, and so on. Just a second definition for it. So now we know an equivalent equation to calculate the thermal resistance of a convection problem. Okay? So, which means that if I want to come to this problem here, the multiple layer conduction problem. So I have 3 layers of solid material. Okay, so this is material 1, material 2, material 3, and I have K1, K2, K3. This is TH. We call that T1. We call that T2. We call that TL. Okay. Then we have three different thicknesses here. L1, L2, L3. Then I told you the inner face of this layer inside the house, if this is inside the house, is exposed to T infinity 1 and H1. The outside face is exposed to T infinity 2, H2. Again, it's always conduction inside the solid body here, but we are getting convection here and convection here because we are associated with emotion of a fluid. So how are you going to present that problem if I ask you to do thermal circuit analysis? Again, let's see. Heat is going into one direction, this way, assuming that T infinity 1 is much, much greater than T infinity 2, as we explained before. So in this case, I'm going to replace each mechanism of heat transfer by a thermal resistance. I have convection, conduction, 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 convection. The simplest way to do that, count how many temperatures you have. 1, 2, 3. I know there is one here, 4, 5, 6. I have 6 temperatures. T infinity 1 is going to presenting the fluid here. TH is going to present that phase. T1 is here. T2 is here. TL is here. T infinity 2 is here. 1, 2, 3, 4, 5, 6. Between each two nodes, you got one resistance. We know this is convection. Why? Because it's happening between T infinity 1, which is a fluid, and TH, which is a solid surface. And between moving fluid and solid surface, that's convection. Through the three solid materials, that's conduction. That's conduction. That's conduction. And that's happening between, that's T1, T2, and TL. Between TL, which is presenting a temperature of a solid surface, and T infinity 2, which is presenting a moving fluid, I'm having convection. That's T infinity 2. Recall, we call that resistance 1, resistance 2, resistance 3. I'm going to call that R node, and I'm going to call that R4. And this is a set of series resistances. And according to the energy balance equation, if I have a steady state condition, if I don't have any internal body heat generation, the energy that's going in has to go all the way the same and go out. So series resistance with the same value of Q. Okay, now we did calculate R1. R1 is conduction. It's L1 over K1 times A. What about R2? We did listed that in the previous page. L2 over K2 A. R3, it's L3 over K3 A. Now, what's new? It's R node, which is a convection, and R4, which is a convection. R node, what is the formula for convection resistance? It's 1 over HAS. It's right here. 1 over H times AS. Okay, so R node will be 1 over R node. It's happening inside the body here, inside the surface here. That's between T infinity 1 and TH. Between these two, I have H1 here. And again, the area will be the same. The area of exposed to the fluid is going to be the same as the area perpendicular to the Q. It's not going to change here. Then R4, in this case, would be the one in this side of the wall. So it's going to be 1 over H2 times A. Now I have all the resistances. What's going to happen? I'm going to only give you this temperature and this temperature. This will be given, and this will be given. What does that mean? If you want to calculate Q, you have only one way to calculate Q. Is to pick two known temperatures, which is going to be T infinity 1 minus T infinity 2. In this case, you have to divide by the resistances or the equivalent resistance in between. So between T infinity 1 and T infinity 2, I have 1, 2, 3, 4, 5 resistances. All of them are connected in a series. I can add up all of them to get the equivalent one. So that's going to be R node plus R1 plus R2 plus R3 plus R4. What you're going to get out of this equation, if you know how to calculate each one of these resistances, if you are given the two terminal temperatures, I can get the value of Q. Now, let's assume I want to ask you to get the interface's temperature. Can you get me TH? Can you get me T1? Can you get me T2 and TL? Yes, I can. I know all the resistances, I know the Q, and I know the two terminal temperatures. Now, the same Q, whatever that number is, should equal to, I'm going to pick this and this. So I'm going to say T infinity 1 minus TH. I will divide that by R node. I know what R node is. I know all the resistances. T infinity 1 was given to me. Q is already calculated from the upper ratio here. So the only unknown in this equation, I can get actually TH, correct? I want to get T1. Okay, one would say, I would take the same value of Q and say it's equal to, I can say TH minus T1 divided by R1, correct? If TH is messed up, T1 is messed up. So I would like to stick to T infinity 1 minus T1. Now I'm between this and this. This is already given. Between these two, I'm going to add R node plus R1. So from this equation, I'm confident I'm getting T1 correctly here. Now let's get T2. How are we going to get T2? The same value of Q is equal to. One would say T infinity 1 minus T2 over this 3R. Yes, that's correct. But why I have to choose the long distance here? I can say it's T2 minus T infinity 2 because T infinity 2 is given. So it's going to be T2 minus T infinity 2. In this case, I'm going to divide between these two values here is R3 plus R4. From this, I can easily get T2 correctly. Now, I want to get TL. Don't pick the large distance. Okay, choose the shortest one. So the same Q can be calculated from the ratio of T1, TL minus T infinity 2, which is already a given value, divided by the resistance R4. I can get from this TL. And now I didn't use any single calculated temperature to calculate the next one. So if I'm messing up the calculation, it's not going to be, like dominoes game here. So it's not going to happen. So I hope that gave you a sensation how simple using the thermal circuit analysis is. Again, imagine now we are going back to using these equations. 3 for the conduction. Then I'm going to have Q is equal to H1 surface area times T infinity 1 minus TH. That's presenting the convection in this side. Now, let's write the equation for the convection in this side. Q is going to equal to H2 surface area, or A, it's going to be the same A, times TL minus T infinity 2. Now, if you follow the old style of solution here, 5 equations in 5 unknown. Go ahead, good luck to solve that in a quiz or in an exam. It's going to take forever, right? Unless you're using like in homework, I can easily go for system of linear equation solver online. I can do that. But what you're going to do in a quiz or exam, you're going to do that in a numerical techniques, it's going to take forever. So that's a bit about the thermal circuit analysis here. I hope, guys, now you digest the how you drive the thermal circuit, how you draw it, then how you use it to actually do a solution in a simple way to your problem. So that's a very simple technique, and it's going to help a lot when we complicate things more with the nuclear fuel. Remember, nuclear fuel has 3 basic shapes. We're going to have plate type fuel. We're going to have cylindrical shape fuel. We're going to have a spherical shape fuel. But all these nuclear fuel, they have Q dot. They have internal heat generation. I didn't talk about how the internal heat generation would screw up this formula here. So I'm going step by step now. So I'm going from using the standard formula for Newton's law of cooling and Fourier's law, how to simplify that by using thermal circuit analysis. Then we're going to complicate that later on. But we stick still for the thermal circuit analysis. Now, what if the geometry we're talking about is not really a plane surface? There's no Cartesian coordinate. It's cylindrical. Okay, again, I'm making comparison here. We are taking a plane type surface because we're going to have a plane type or plate type fuel. We're going to do cylindrical shape because we're going to have a fuel pin fuel or a cylindrical fuel. And then I'm going to do a simple sphere because we're going to have nuclear fuel spherical shape. So step by step here. Again, remember, this is a basic course. Some of you doesn't have nuclear engineering background. Some of you already covered the heat transfer course like long time ago. Some of you are actually coming from non-engineering background. So I'm trying to be very simple, explain the concept so you guys can actually keep up with the course content.